Howdy guys, today we will be talking about Dijkstra's algorithm. So what is Dijkstra's algorithm? Dijkstra's algorithm finds the shortest path from one node to another, given a graph. So let's say you're at an airport and you want to know what the fastest path is from, or the cheapest path, should I say, is from, let's say, Austin to Seattle. If you run Dijkstra's algorithm on the entire network of the airports of when airplanes are leaving and going, you will find the cheapest flight from Seattle to Austin, or from Austin to Seattle, sorry. Notice how Dijkstra's algorithm works very well with weighted graphs. This is very important. Weighted graphs is where Dijkstra's algorithm truly shines. So notice how I specifically said cheapest flight. When Dijkstra was looking through that entire network of airports, it held into consideration the weight of it, that is the price of going from Austin to Seattle. It took into account that. So it didn't necessarily just send me straight from Austin to Seattle, because that's not necessarily cheapest, although it's like the first result found. Like, let's say here's Austin and here's Seattle, and here's layover right here. It didn't just necessarily just send me in here. It didn't just assume that. It also checked this 2-point layer of path. Because let's assume this was like $1,000 and this is like $5 and $5, you know? In this case, Dijkstra's algorithm would find that the cheapest way to get from Austin to Seattle was actually through this 2-point node. It is extremely important. This is like the crux of Dijkstra's. This is unlike breadth first search, where breadth first search doesn't really deal well with weighted graphs at all. Like, breadth first search was made as a traversal algorithm. So what this means is that the point of breadth first search was to hit and see all the nodes. As a helpful little side effect for us, it finds the shortest path in unweighted graph just by the nature of how it works. But it wasn't made to find the shortest path. It just so happens that it does. Dijkstra's, on the other hand, is made to find the shortest path with weighted graphs. It's important to note that it can also find the shortest path in unweighted graphs. It just will consider everything as a weight of 1. Also, the next point is that it does not work with negative weights. You cannot have -10 or -20, and so on and so forth. You will get a result, and if you just implement Dijkstra's algorithm without any like error checking, like, it won't send you an error, but the result that it comes out with will not be accurate. So please pay attention to make sure that there are no negative weights in the graph that you're doing. That's a common quiz or test question, in that which one is better? Can Dijkstra's algorithm work with negative weights? And the answer is no, it cannot. So let's do an example, because I feel like we all learn better with examples. So let's run Dijkstra's algorithm on node A. So it'll be this one right here. And what Dijkstra algorithm will return is basically the shortest path from A to every single other node. So it will find the shortest path from A to B. It will find the shortest path from A to D. It will find the shortest path from A to C, and so on and so forth. So let's start running this. So how Dijkstra algorithm starts working is with a priority queue. So I have already filled in this first line. So what does this line mean? Let's go through it one by one. So this column is just basically the iterations. It's just counting. That one's pretty self-explanatory. So this one will basically keep track for us the popping. So how Dijkstra algorithm works is that when it finds the shortest path and it determines this path is the shortest and no other path will ever beat it, then it's just going to pop it into here. And then this the rest of this line will be basically have this format. It will have a number, and then it will have a node. This number right here represents the weight or the value it took to get to this node. So this will become clearer as we go on. And then this node represents its predecessor. So again, this will also become clear as we go on. I won't spend too much time on this specifically, just because I feel like as the examples go on, hopefully you'll be able to understand, but we will revisit this at the end. So in this first line, we see that we already have this one filled in. And this is because we're determining how long does it take to get from A to A. And obviously it takes 0 time to get to A from A because like it's right here. And the predecessor is A. The rest of these are infinity because we have not determined a path. We have no idea at this point where B is. We have no idea at this point where D is. We have no idea at this point where C is. But we do know where A is. So now what we're going to do is we're going to pop A. And we're going to pop A because it is in our priority queue. It is the shortest path. Like obviously 0 is less than infinity, infinity, and infinity. So we're going to pop the minimum, which is A, and we're going to put it right here. Now we are going to determine from A, we're basically going to consume A. We are going to determine the path from A to every other path. So we're going to go to C. We also can hit D, and we can also hit B. You basically fan out and hit every node, basically investigate every path starting from A. So let's start with B. Okay, first of all, let's look at A. Since we have already found the shortest path to A, we're just going to put a little dash there. I mean, clearly there will be nothing faster than 0 and A. Like, that's impossible. So we're going to put a dash there. We're done with A. A has been completed. We have found the shortest path to it, so we don't even have to worry about it anymore. Next, let's determine this B. Okay. This B, we're going to have our little thing. So we're going to have a number here and our node letter in the parentheses. So it takes a path of 6. As you can see right here, it takes 6 seconds. I'm going to assume this is in seconds now. It takes 6 seconds to get from A to B. So that's all we're going to put. We notice that 6 is less than infinity, like this infinity right here. So we can determine that this path is most certainly shorter than infinity. And the predecessor is just like what node it had to hit before it hit here. So that's just A. Because we noticed to get from 6 to A, we had to follow this path. And what's behind this path, what's on this opposite way, it's A. So let's do the same thing for C. And we're gonna look at C only because we can hit C from A. This is the only reason. Notice that if this line did not exist, like at all, we would not be dealing with C right now. We would just drop down this infinity. We are consuming A, remember that. We are evaluating A, all the paths from A. But since C is hit from A, we can just take that. And once more, we can see that the path it takes, the number, is a value of 3. 3 is certainly less than infinity, so we're just going to put 3A right here. Okay, wonderful. Now we're going to do the exact same thing with D. Nothing new here. The path it takes, the predecessor is D. It takes a path of 7. 7 is certainly less than infinity, so we're just going to write that down. Okay, what is the step that follows? The step that follows, now that we have determined this entire line, we have filled in our entire chart, we're going to pop something. we're going to see what the shortest path is. And the shortest path here is, as we notice, the minimum is this 3a. So we're just going to pop C. Okay, why? Why did we do that? How Dijkstra's algorithm works is that basically from A to 3C, you are guaranteed that no other path will ever hit C faster than just directly from A to C. Why? Well, it's impossible going, let's say, from A to D and then D to C. Let's take this example. You don't even have to know whether D to C exists. We know there is a 7 right here, yes? And 7 is greater than 3. So how in the world will a path be found to C that's shorter than this path right here? How is that possible? How will a path be found that's shorter than 3 if we go to A to D first? It's impossible, absolutely impossible, because we know that as we go down this path, the path will only increment. That's why when we're looking at these 3 values, we're guaranteed that nothing will hit C faster than this minimum. Now let's assume this was instead 1. Yes? If this was 1, we could be guaranteed that there's a path faster than to C from A. Because we could hit here 1, and then 1, and 2 is less than 3. But because it is 7, and your path will only go on incrementing, then we know then this minimum right here, we know that's absolutely going to be the shortest path from A to C because it is the minimum. Oh, I erased something I shouldn't have, sorry. Oh, there you go. Sorry, there you go. So that's basically the essence of Dijkstra's algorithm. This is how it's working. Now notice that the assumption that it makes. The assumption that it makes is that when it looks at all these minimum values, it makes the assumption that when it finds the shortest path, this minimum, that no other path will ever go faster to it. But this is all null and void if there are negative weights. So understand, let's say this was -10. Now we do see that there is a shorter path from A to D. And this will be from A to C, sorry. And this is the path from A to D and then D to C. Because now we will have a total path of -3. And this completely destroys the very logic and that Dijkstra hinges on. So that is why negative weights don't work, because Dijkstra makes the assumption that whenever it finds the shortest path, the minimum path, that no other path will beat it. Okay, let us continue forth. Right now, we're gonna, right here, we're dealing with C. So here, we're just gonna look at C. We have consumed this path right here. So right now, we just treat it as null and void. We ignore it for the rest of this iteration. Once more, we're gonna bring down this dashed line here. And since we just popped C, it no longer is in the priority queue, so we just bring down a dash here. Okay, so now let's go ahead and deal with C. And there's only one path going from C to D that hasn't been consumed yet, and that's from C to D. Now here's what we're gonna do. We're going to be dealing here. We're going to determine, is it faster going from A to C and C to D, or is it faster just going from A to D? Now, this is pretty simple, comprehensive to understand how. All we're going to do is we can compare this 7. This 7 we know is the current shortest path that Dijkstra has found. So we understand that this 7 is the shortest path it has found now. Now let's compare this with the shortest path that we are finding now. The shortest path that we're finding now is going to be 3 plus this path. And the reason is this 3, what this 3 represents is that it takes, let's say, 3 seconds to go from C to A. So all we're gonna do, there could be like a million nodes here, yes? But we don't care. All we care is how long it took in total to get here. So it took 3 seconds to get there. So all we're gonna do to determine it is gonna do 3 plus 1, because it took 3 plus 1. We see that that is a total path of 4. And we notice that this is now the new shortest path. 4 is indeed less than 7. So now what we're going to do is going to do 4. And what is the predecessor? We have found that the predecessor is C. We can get to this path of 4 if we hit C beforehand. Okay, wonderful. And let's take away, and B has like no shortest path that was found for B. So we're just going to bring that down. Once more, we're going to compare these two. There's this 4, and then there's this 6. So let's see. This 4 is going to be this minimum priority queue. So what we're going to do is we're now going to consume D. Yes. As we've been establishing, because we consumed it, all we're going to do is dash it. And we have here. Now we're going to determine from D to B. Yes? So once more, we're going to do the same thing. We're going to do 1 plus whatever value is here. So in this case, it's going to be 4. 1 plus 4. Because this is, again, this is the value it took, the path. This is how much time it took. It took 4 seconds to get to D to A. So we're just going to see from D to B, is that faster? We get 5. We see that this is faster. So we're going to do F. And how we got there was first going through D. So we're going to put that in there. And finally, the last thing, we're going to just pop one last time. And that's just going to bring us to B. And we have consumed everything. So now we see the shortest path from every single node. So let's go ahead and go through it. Here is the shortest path. I'll highlight it for you guys. So first you start at A, then you go to C, then you go to D, then you go to B. Now this is the shortest path to hit every single node. If you want to get to D, you have follow this path and you got there shorter. If you want to go D, follow this path and it'll be the shortest path. If you want to get to C, then follow the shortest path and you will get there. And that's how Dijkstra works. Let me make one final note on these predecessor nodes. We see with these predecessor nodes, you can basically, there's a lot of information being held in this chart right now. So with these predecessor nodes, we can notice, we can build this path without using this. So technically this line isn't necessary because all you do is you're going to look at the last thing consumed each time. So this one, and then like basically I like to look at it, what's like the thing that gets dashed. So here, and then here, and then here. And it's because this is the last item before it gets dashed. This is the last item before it gets dashed. This is the last item before it gets dashed, and so on and so forth. And now we can just basically follow that. So we start at B, because B is right here. And then we go to its predecessor, so D. And we're going to look at D, its predecessor is C. And we're going to go to C, its predecessor is A. And then that's the shortest path. Notice here, it gives us the exact time it takes. So it takes 5 seconds in total to get to A from B. It takes 3 seconds from C to A, so on and so forth. And yeah, this is the final chart right here. And thank you. I hope you guys learned. And yeah, have a nice day.